So every time that you have a problem that belongs to the combinatorics area, the basically the counting methods and how to calculate how many ways you have in order to solve it. And this is important because in order to calculate probabilities, you really have to calculate how many ways you have in order to create an event. You have to ask yourself how many total elements we start with in the group. So, for example, you want to see how many ways you have in order to choose an outfit. Okay, the first thing that you need to know is how many pants and how many shirts do you have to choose from. Okay, this is the total number of elements. Then you have to, you start with the order. The first thing that you want to know is if the order is important. Okay, if you answer yes to that, if the order is important, then you have two issues. How many elements you have in the group and how many positions are that you want to put them. Now, how do you know that you have positions? If the order is important, then you have some order. So I want to see in how many ways I can arrange 3 students in a classroom next to each other. Well, the order is important. How many chairs do I have? 3. How many students do I have? 3. So the n is 3, the r is 3. Okay. In this case, and when the order is important, immediately it means that we deal with permutations. If the order is not important, then we deal with combinations. When the order is important, and because we have we have more ways of rearranging things, because the order is important, then the permutations, they always give us bigger numbers as solutions. The combinations, the results that we get of the events, of the counting events, is going to be a smaller number. So combinations are always less than the permutations. So when the order is important, okay, we decide how many elements we work with and how many positions we work with. Then another question that we want to know and we ask ourselves is, are there at least r copies of each of the n elements? What does this mean? Well, what this means is that do I have enough elements to cover all the positions? So, for example, if I say I have 5 chairs, but I have 2 students to arrange, then I don't have enough elements to put in all the chairs. So immediately I need to work with this problem in a different way. When I do, then I have to work with a different way again, and I have a different formula to perform. So I'm not going to go through the entire diagram, but I just gave you the idea behind of these questions that you need to ask yourself in order to decide what formula you use every time. Okay, it is helpful. Now, the complex problems in combinatorics in general are problems that they have more than one tier. They have 2 or 3 or 4 tiers. What does this mean? Things are happening, and we don't have one situation. We have more than one situation. If the situation that we're trying to resolve is complex, then what we need to do is find a way to divide it into levels. Now, I'm pretty sure that you have already worked with decision trees. So, and this is how we deal with these type of problems, the counting methods problems as well. We try to set up a decision tree and split the complex problem into tiers based on how we want to come up with our results in the decision. A simple permutation is solved like that. You know already this. This is an example of a permutation, and so on. Find the number of ways of forming 4-digit codes. Here, definitely the order is important. We have how many different digits? 10, so more than 4. So we have enough numbers in order to cover the 4. right? So this means immediately that you need to select 4 digits from the group of 4, first of all, and then arrange those 4 digits in the order. We use the formula 10p4, and the formula 10p4 is n factorial divided by n minus r factorial. And this is how we get our numbers. Immediately, the order decides the formula that you use. This is what you need to have in mind. Another example similar to that. Now here we have a different situation that is a special situation, and in this case we have many groups of elements. The classical example for this type of problem is I'm not gonna, yeah, let me a moment. The classical example for this type of problem is the word Mississippi. How many different words can you make from the word Mississippi? Well, what happens here? We have 4 S's, 2 P's, and 4 I's. No matter how we will rearrange 2 I's, if we put them in order, I, they are the same letter. So although that we have order, we have to consider the situation where we have a group of elements and they are the same mainly. The formula that you see on your screen is the formula that you need to use in these cases. I'm sorry for that. Just a moment. So Mississippi has 10, I think. Mississippi has 11 letters. So the n is 11 in this case, 11 factorial. And on the denominator, n1, n2, and 3 describes the number of letters that we have in each category. So we have 1n, we have 1p, we have 4 s's, and we have 4 i's. So the n1 will be 1, the n2 will be 1, the n3 will be 4, and the n4 will be 4. So we will divide the 11 factorial by 1, 4 factorial, and 4 factorial. And just reminding you this because this is actually appears in many different problems in the book as well. Okay, and this is another similar problem that is an application for that. And then we come to the combination. The combinations are easier. They are focused basically on problems that order is not important. What happens if order is not important? Well, if I have the 2, let's say, letters, A, B, and I want to know how many different 2-letter words can I make from A, B, if the order is not important. So if I want to put them in a set, in how many different sets can I put them? Well, the answer is 1. If I have the A and I have the B and I don't care about the order, I have only 1 possible set of ABs. If I had to permute AB, then I would come up with 2. So you see, permutations are always more than the combinations. So this is what I wanted you to realize. And the formula to calculate those is this. Okay, and here I have a few examples on one tier and more complex examples. I have 3 more complex examples that you can review them. I will share those with you and ask me if you have any questions on permutation combinations. But the formulas, the basic formulas that you need to remember are the ones that I already showed. Any questions on that? Okay. The moment I want to see if I have the binomial distributions along with everything else here. Okay, so Again, I trust that you already took the predict 400, so I'm not going to go through these, through what you see on your screen step by step, because you already know what event is, what is a simple event, what is a sample space, and so on. You did it in week 3 and week 4 in your previous course, but I want to mainly focus on some important, um, 2 or 3 important different terms. And these ones are going to be the addition rule. And what the addition rule is that when we have when we have two events and we want to find out what is the probability of the one or the other, then how we calculate this probability. In order to calculate this probability, we need to know one thing. We need to know if the events are mutually exclusive or not. If the events are mutually exclusive, then the probability of A or B is equal to the probability of A plus probability of B. You need to remember that. If the events, though, are not mutually exclusive, then what you need to calculate is the probability of A, to add to that the probability of B, and then subtract the probability of the intersection of those two. So this is extremely important to remember. The addition rule, it has different results based on the type of events that you have, if they are mutually exclusive or not. The general rule is the one that you see on your screen. P of A or B is equal to P of A plus P of B minus the probability of the intersection. Okay, if you look at this at the Venn diagram, you will see right here that in the case that we don't have mutually exclusive events, here are the mutually exclusive events where the one happens, the other happens. There is no way that both of them can happen at the same time. Then definitely, if I want to find the probability of A or B, then I will consider the probability for the event A, and then I will consider the probability of event B and add them up. If not, if they are not mutually exclusive, then they have some kind of intersection. So this means that if I add the probabilities, I need to subtract the probability of the intersection once, because I have considered it for P of A, I have considered it for P of B. So the probability for the intersection, I counted twice. That's why I have to subtract it once right here. So that's the one thing that I want to remind you. The others, I'm sure that you already remember them. The other thing that I want to remind you is the difference between dependent and independent events. Two events are independent if the occurrence of one doesn't affect the probability of the occurrence of the other. Many students confuse still the difference between mutually exclusive events and independent events. These two terms are different. Events are independent if the one doesn't affect the other. Can they happen at the same time? Yes, they can. So they are not mutually exclusive, because mutually exclusive events are events that cannot happen at the same time. So this is the difference right here. So what is the probability that, I don't know, butterfly flies in Japan and this causes a problem in New York metro station? None. These events are independent. The probability that the butterfly flies in Japan and the probability that the metro, the whatever subway runs in New York, they are independent. The one doesn't affect the other. Okay? Can they happen at the same time? Yes, they can happen at the same time. So basically, this is what I want us to make sure that we understand. Then comes the bias theorem. And the bias theorem is a theorem that is extremely important and quite confusing. The bias theorem is quite confusing in terms of its calculation. Because of that, I have created a video for a bias theorem example and how to solve it using a diagram. In our class, except of the bias theorem, we are going to review also the generalized bias theorem. What is this? Well, the generalized bias theorem is the same kind of theorem, but at the denominator, we consider more than two events. If we have more than two events to consider, then the denominator has more terms right here. Similar type of terms like this, but more. Can we have 3, 4, 5, 11, 100 of them? It doesn't matter. This is what the generalized bias theorem. Now, because we don't have too much time to go over this in detail for the bias theorem, I have created a video for you, and I also have created an example for the generalized bias theorem. I don't have it in the handouts now, I remember that. I usually post it in the question and answers area, but I'm going to add it in my handouts and share it with you. Okay. The reason that I'm not going to spend time right now in bias theorem is that I want us to go through it. If we have time, we will go through it after we see the binomial distribution and the Poisson distribution. But I have the video to cover you for later. And at the same time, I have the detailed example that is an actual problem from your book that I have solved for you. So I will share that for you. And after you have worked with the bias theorem, next week, before we start the class, I have planned to discuss with you the importance of bias theorem. But right now, since some of you may not even remember what this thing is, it's not going to register. It will be better if we discuss it next week. That's why I'm telling you that the bias theorem for you is extremely important, first of all. Why it is important? It is important that because some of you may have already heard the Bayesian theory. The Bayesian theory is extremely important for data analysis. You can even take an entire course in Bayesian theory and how this applies in our area. There are machine algorithms that they are using the Bayesian theorem. What is this about? Well, it's a simple situation, basically. How do we find the probability of an event? Well, we count the many different ways that this event can happen, and we divide it by the number of all the possible ways of the entire sample space. With but sometimes, and in real life this happens many times, we have information about the sample space that can help us limit the denominator of the probability. What does this mean? We have background knowledge. If I have background knowledge, then usually the probability that I will calculate after using the background knowledge will become higher. What does this mean? Okay, let me give you an example. I want to find how many different, let's say, female students are in MSPA program. Okay, what do I have to do? I count the number of female students, I count the total students, I divide those two, and this is the probability if I pick a student to be a female student. Okay, now assume that I do that in a generalized machine learning algorithm where I want to identify the different trends of the students in the MSPA program. And I need to focus after different steps of my algorithm on the female students. But not all the female students. I want to focus on those students that they are, let's say, second semester students, second session students. Okay, the probability that a student in the second session takes 401 is very high. It's 98%. Immediately, this means that if I want to focus on students that they are on their second quarter, and I want to focus on the female students that they are on the second quarter, I can use the information of how many students take the 401 class in order to find the probability of the students, of the female students, and the second quarter. This is background knowledge. The background knowledge consists of the fact that I can look at my second semester by focusing on 401. And then what happens is that if I pick a student now, and this student comes from the second semester student, then I want to find out what's the probability that this is a female. What happens here? What happens is that I'm going to make smaller my denominator. Instead of having all the MSPA students, I will focus only on the students that they are in 401. The probability of picking up a student who is a female now is going to be higher because the denominator became smaller. The prior probability is the initial probability. What's the probability? The probability value of finding a female female student if I look into the entire MSPA program. The posterior probability is the probability value that has been revised now using the additional information. Now, I know that the student that I'm looking for is a second semester student, so the probability that I will calculate will be the number of the female students divided by those that they are in their second semester. They take 401. This is the posterior probability. So working with prior and posterior probabilities, they help us identify conditional probability that you already know about that. Sometimes though, I have to reverse information and look at my posterior probability in order to calculate my prior probability. And this is where I use the bias theorem. And the bias theorem is a very, very, very helpful theorem, but quite confusing. And when I say confusing, it is confusing because it's long. And very few students remember the formula. Now, it's not difficult, it's not challenging, it's just long. Pay attention to the details, understand what this is, and also look at, and I think I have it right here, and I will share it with you in a moment. Look at the details, look at the decision diagrams that I have prepared for you. Where is it? I don't have them here, I don't have the... No, I don't have the decision diagram right here. With the decision diagram, what we do is the following. We create on the top of the diagram of the tree, we enter the probability, the prior probability. Here it is, I found it. So let's look at this example. We have 51% that are males and 41% that are females in a sample. It is later learned the survey subject was smoking a cigar and 9.5% of males smoke cigar, while only 1.7% of females smoke a cigar. Let's look at the problem that I have prepared for you right here. Here it is. So we get the idea. To find the prior probability here is not difficult. We want to find the prior probability that the selected person is male. Well, there are 51% male, so the probability is 0.51. Now, the second step, the B, is what gives us the posterior probability. It what gives us the prior knowledge that we have in order to calculate the posterior probability. What it says is that it is later learned that the survey subject, the person that we surveyed, was smoking a cigar. And because he was smoking a cigar, we know now more information about that. 9.5% of males we know that smoke cigars, while only 1.7% of females smoke cigars. Now we want to find the probability that is male again, whatever we found for A, but given this extra information. And I have solved this problem by setting up the information right here for you, and by just calculating the probabilities for each one of these events and applying the theorem of bias, the bias theorem, and the formula as it is. Now, on the next step, instead of doing that, what I do is I create a decision tree. The first step of the decision tree, the first level, gives us two branches. The first branch gives us the probability of the event of being male. The second is of the event of being female, the prior probability, right? The first step, the prior probability. So the probability of being male is 51%, the probability of being female is 49%. At the second level now, I consider each one of the posterior knowledge that I get. That is 9.5% of males smoke cigars, 1.7% of females do. So on the second level of our tree, you see that I post the probability of smoking, given that is a male. And why do I have this here? Because this is the branch of males. So at the next step, I split them to those that they smoke and those that they don't smoke. And I enter the probability for this. Same thing with females. Here I split them to those that they don't smoke and those that they smoke. You see the conditional probability here, probability of smoking given that is a female, times the probability that is a female. This gives you the probability of being what? Being a female and smoking. Remember, this is the formula from the conditional probability. The conditional probability tells us that P of the intersection of two events is equal to the probability of one event and the probability of the other event given the first event. This is what we have. So, if you take the multiplication of these two, this is nothing else than the probability of smoking and being a male. But at the same time, graphically, you can see that if you do that, you multiply the probability of that, you multiply the probability of that. So every branch of the tree has a meaning now. It is something specific. Not only has a meaning, but the other beauty about this thing is that these branches right here are part of the formula. So what is this? This is the probability of being a male times the probability of smoking a cigar given that being a male. So if you come here, it's this. So this part, the numerator, and this part of the denominator can be found right here. That's why I'm telling you, if you put things in a decision tree, it's much easier to understand what you're doing. Now, it is extremely important to use the decision tree, in my opinion. I'm a visual learner, because when you work with a generalized bias theorem, you are going to have much bigger decision trees. And usually, the breadth of the tree is what is bigger. You're going to have many more levels at the second level of the tree. Okay, and it's much easier to see what you need to add right here in order to create your formula. So at this level, if you want, the question that we were asked is to find the probability that the person is a male given that he is smoking a cigar. So the probability of being a male given that he's smoking a cigar is going to be the probability of smoking a cigar and being a male divided by the probability of smoking. And this, if you analyze this, this is this. How do I know that the numerator, probability of the intersection of the two events, is that? That's the formula. This is the formula that you already know. And the denominator The probability of smoking a cigar is what? Well, he's going to be either a man and smoking a cigar or a woman and smoking a cigar. This is what this says. The probability of being a male and smoking a cigar, given being that he's a male, and the same for the female. So this is simply, it's just the analysis of that. Now, if you look at your tree, these are the numbers that you find. This is your numerator, okay? And the numerator is nothing else than this part of the denominator. And this right here is this part of your denominator. That is everything about women. You add those up and you come up with your result. That is 0.51 times this, 0.49 times this is your denominator. You add them up, it's going to give you the denominator. And this, it's by itself, is the numerator. If you go back to this slide where you just applied the formula, it tells you the same thing. And that's the answer. So Bayes' theorem, it can be confusing if you don't understand the formula. You need to really get the formula. Let's go ahead then, skip the rest, and go directly to binomial theorem. First of all, last week, we were talking about distributions. We talked a lot about distribution. I gave you in detail and I explained you how to create the frequency distribution graphs. And I said that we definitely really need to understand those and really need to understand not only the histograms, how we create them, what is the best way to create them, how to split them into different classes, because these are things that you will be doing by yourself as a data scientist. You will making the decisions on how to do all this for the best presentation to the others, but also to yourself in order to analyze at the phase of the analysis of your distributions and data sets. Now, today we are going to work only on discrete distributions. Distributions that they have to do with discrete variables, meaning variables that they take values as 1, 2, 3, 4, 5, and so on. And then, I'm sorry, we are going to work on continuous variable distribution next week with the normal distribution. The first and the simplest distribution is the binomial distribution. We will come back to that in a moment. Go directly to the binomial distribution. The binomial distribution, the binomial probability distribution, first of all, has specific requirements. It's not hard. I don't believe that you will find challenging to understand when to use a binomial distribution, when to use a Poisson distribution, or when to use a hypergeometric distribution. But it may take some time to be able to recognize a problem. You may, maybe at the beginning you will not be able to recognize the problem immediately if it belongs to the binomial distribution or to the Poisson distribution or to any other. This takes practice, just practice. At the beginning it's not going to be that obvious, but later it's going to be much more obvious. One thing that I want you to understand is that although we may have situations where it seems that the distribution that we have is binomial distribution, if still it is possible that it's not the case. And in order to ensure that a situation, and I'm talking about an experiment basically, follows a specific probability distribution, like the binomial distribution, it means that it needs to follow, it needs to abide on specific requirements. The requirements are the ones that you see on your screen right now. The procedure, the experiment, has to have a fixed number of trials. The trials must be independent. meaning the probability of the one of the trials to have a specific result and the probability of the next trial to have a specific result should be independent, shouldn't affect the one or the other. The third requirement is that each trial should have only two possible outcomes. And the fourth is that the probability of success is the same for all trials. Now, in many cases, we have distributions that they are not binomial distributions, but they can be approximated by a binomial distribution. I'll give you an example, because I'm not going to go through step by step how to calculate it. This is very simple, and I will tell you how